Okay, so let's work on the Euler method. It's Euler like the old football team that ditched Houston in the middle of the night. Not Euler, you'll sound uneducated. So the Euler method, and this is an integration method. What is it? Well, if you look at the blue curve here, that's kind of the original curve. And what you see here is this kind of jaggedy approximation. It's not perfect. And at the beginning, it's perfect because that's the data point we know. But as we go away from it, you'll see that the error gets larger and larger, and eventually it becomes useless. And so the idea here is to make an approximation that'll kind of follow the curve. And you'll see pretty soon we're gonna use something called Runge-Kutta that hides very well next to it. But this is a great method that's kind of a basic and a foundational one for these types of problems. So what does it do? Well, let's start off with the definition of a derivative. Now we're going to start it off without the limit here so that you don't have to worry about the limit. And what we do is we multiply both sides by h, right? Then we're going to move the f of t to the other side. And what we see is that the next point equals the current point plus h times the derivative, and so that's what we set up here. So we're going to use fty to be the actual derivative. And so this is what we're going to use for the Euler method, and what it's going to allow us to do is step through the y values that we're interested in. So how does this work? Well, we define the two endpoints and the number of steps that we're going to take, or the number of rectangles we're going to use in our approximation. And then we go ahead and just set it up with the known approximation. We calculate the height of each rectangle, or the distance, the width of each rectangle. We set that up as a time basis. That's going to be the x-axis. We calculate the error, and then we set up our real solution. Now, in actual practice, you're not going to have the real solution, but in this case, we're going to set up one so we know. What we're going to do then is we're just going to cycle through and go ahead and fill up these vectors, and when we're done, we're going to go ahead and output. There's a little bit of a trick here that if you're going to do 10 steps, you want 11 spaces, because the first one is like your 0th space, okay? So that's kind of the idea here. It shouldn't be too bad. And what we're going to do is we're going to use this here pseudocode, again, out of a Numerical Methods book. I've touched it up a little bit, and this is the one that we're going to use, okay? So let's go ahead and try to use this and encode it in MATLAB. What do you think? Oh, I had a problem that I wanted to solve. So here we go. We've got ours, and let's open up MATLAB here. And we'll give us a decent space to work on. And there's a couple of things. One of the things is right away, we want to go make us a function. So let's go make a function. And it's going to be dy dt equals a function of t and y. And it's going to have to take in a t and a y value, I believe. Okay, so what we're going to have here is we're going to pick out our function. I'm going to choose one, so I've got one here that I want to do. Dy dt is going to equal, and it's going to be y minus t squared plus 1. Okay, so that's going to be the function, and we'd end that. Okay, so now we're going to just go ahead and save this. And that's going to be my function file that we're going to use. Now over here, we're going to go ahead and set this up. So there's going to be an Euler's method. And this is, let's say what it's used for. It's used to approximate f prime of t and y, right? Equal to y prime with y of 0 equal to alpha. Okay, so with some initial condition. So it solves a differential equation with a given condition. We're going to use n plus 1 equally spaced items. So we've got our endpoints. So it's going to tell me here from 0 to 2. So we're going to have a equals 0. So this is the, sorry, I typed C++. So this is going to be our left time endpoint, which often you'll start from time equals 0. B is going to be your end time, which is going to be 2, usually in seconds, right? But it depends if you're in CGS units. So this is going to be the right time endpoint. Okay, so that's what those are. Now it gives me that n equals 10. So this is going to be the number of rectangles or number of steps. And then alpha equals 0.5. And this will be the initial measurement or initial condition. Okay, so those are the things that we know. Now, there's some other stuff that we want to set up here, and that's going to be in step 1. We want to go ahead and set these up. The other thing we want to do is set ourselves up to gather all of this information into vectors as we calculate this, because we're going to want to plot this. So I'm going to have a W vector, right? I'm going to have a Y vector. And I'm going to have a t vector, okay? And you can name these other things. I've chosen to name it like this. I have a certain naming scheme I tend to use. So this is the approximate solution. This one's going to be our real solution. So we had to be given this, or we have to go find it. I'm going to hook you up with a differential equation solver for your homework. And then, like the Wolfram Alpha style, you know. And then this is our time vector. Oh, and these are vectors, not just so that we can have like a table of these values, right? Okay. So this is going to be to set up vectors. That's what that is. Okay. So cool. Above that we want to go ahead and set up set up our initial conditions. So, oh, and it wants to put alpha in here. I'm okay with that. So let's put alpha in there. Let's set h equal to b minus a divided by n. And you'll notice I actually have all of that, right? So this is the width of each rectangle. If you remember your Cal 1, right? And then it says t equals alpha. I'm going to do that down here, okay? So look, W vector at the first location needs to equal alpha, right? Because that's initial condition. The y vector at the first space also equals alpha. We know that. The t vector in the first position is equal to a, because that's the left endpoint. Okay, so those are the three vectors that we wanted to set up. And that gets us through step 1. Okay, now step 2 is we're going to actually start computing these. So I already know W1, so I know the value for 1. So now I'm actually going to use a for loop instead of a while loop. So this says even for I goes from 1 up to, no, from 2 up to n plus 1. So actually, instead of using blank vectors here, you know what I'd like to use is a zeros vector of n plus 1 rows and 1 column. And that'll make everything easier for me because it's pre-allocated for space. I don't know if you would notice that on these fast computers these days, but there's some other advantages. I already know what space these are going to be. So I've filled in the first space, right? So I have n plus 1 spots to fill in my columns. So what we're going to do now is we should be able to set this up. So the W vector at the ith position, right, equals the W vector in the I minus 1th position, which is really important that I started from 2 because I minus 1 will be 1 and I have a first position in my vector. In MATLAB, if you try to reach the 0th position, it'll screw up. Python does something different. We'll cross that bridge later. Okay, times h, which we've calculated above. times f of t and w. And I have this over here, ty, right? So it's going to be fty. And what are we going to pass through? Well, I need to pass through a t value and a y value. And here the t value is going to be the t vector at the I minus 1th location. And the y value is actually going to be the w vector at the I minus 1th location. Okay, so that is this formula right here written in vector form. Okay, and it tells me which position. Now I don't have to worry about the comma 1 because all of them are comma 1, but if it was comma 2 or something like that, then I would need to specify which column it was going to be in. Okay, so there's that one. I happen to know the y solution, so let's go ahead and set that one up as well. Oh, I might need that after this. So t vector at the second position is a plus I times h. And I don't have to do anything extra there. So that's the first spot, which in this case is going to be 0, plus I times, so this will be like an integer, 1, 2, 3, 4, 5, and it'll start with 2 actually, times h. And do I have to step back one? No. Okay, so I don't think so. We'll figure that out when we get there. So now at this point, the y vector, we should be able to calculate. I know the actual solution. See, I cheated. I know the solution. Okay, so this is going to be the t vector at the I position. And then you don't do this for E. You do exp. And you don't put a caret. You don't do it in Excel either. To the negative t vector of I. And that should work. I'm going to claim it works. We'll see what we look like. Okay. That's it. Okay. Once we're there, we end this loop. Okay, so we've calculated the new w vector, which is going to be the new approximation, the new time value, and maybe no, it's fine. And then the current actual solution, and we could do this vectorized. So if you don't like it in here, that's fine too. Okay, we're going to output t and w, and we're going to stop. So what we would like to do, I mean, we can output it. So how did we make a table before? Do you remember? Let's do that. And then we want to plot it. I want to plot it first, actually. Can I plot the t vector against the w vector in a red line for Texas Tech, and then we'll do the t vector against the y vector in a blue line for University of Houston Clear Lake. And I won't write all these labels and titles and such yet. So this is going to be the Euler method. Okay. They don't look qualitatively similar. Something's wrong with it. They start off at the correct point, and it's possible this is it, but this one I think should follow the behavior. The blue line is the real curve, so I tend to believe that to be correct. So let's go see what we might have done incorrectly in here and see if we can catch a mistake. So it equals a previous value plus h times the t vector at the I minus 1th and the w vector at the I minus 1th. I wonder if this is supposed to be I minus 1. So I was wondering this. Because at the second spot, we're not 2 in. We're only 1 in because we started at the 0th. And that looks a little bit better. Let me double check this real quick. Okay, I found my mistake. I shouldn't have had a negative sign there. Freaking negative sign. Okay, do you see how over time it falls away from the actual solution? So there we have that. Now, so I didn't change anything else in the code, just that errant negative sign. Let's go get an X label. I think we can do this. I put time there, and I think we can even change the size. Y label, let's put Y value. I don't know what to put there. Solution. And there you go, time and Y value. Let's put a title on it. Title. Okay, so now we have this chart put together, right? So we can now put a graph. And then let's make it so we can output a table as well. Table of tvec, wvec, and yvec. And how do we do this? So then we're gonna write table. Is that what it was? Oh, it did. T and then a file name of Euler solution output, I don't know, .xlsx. And if your computer's freaking out, like you have a Mac and it doesn't know where to put this, you can put your whole, like the whole address there. Just be careful if you're doing it through the iCloud. It gets a little bit tricky. Maybe I don't care. What do you think happens if I do this? It didn't yell at me. So now if I go to our class, oh, I don't have my solution. What happened? Oh, where are we saving these? They're on the desktop. It's not in here. There it is. Bam. Thing looks great. Okay. And there you go. And then you could actually plot these here as well. I like my MATLAB plot. It's cooler. Okay, so there you go. Try it on your problem.